So I've been playing around a little bit with Conway's Game of Life. This is a pretty straightforward mathematical setup that mathematicians have been wrestling with for a while now, where you have a grid of dots that are either alive or dead. You start it with a certain number that are alive, otherwise nothing much interesting happens. And basically, if a living dot has fewer than 2 or more than 3 neighbors, it gets switched off. It dies. On the other hand, if a dead dot has exactly 3 living neighbors, then it comes alive. And you can get all these neat, interesting patterns. This is kind of the classic glider because it repeats itself and moves along here. So it's this kind of living system that can move along here until it gets to the edge of the grid. And again, it's following that rule where 3 living dots will turn on a dot, and fewer than 1 or more than 3 neighbors will deactivate a dot. And you can end up with these neat equilibrium states where you have things like this 2 by 2, because each of these has 3 living neighbors. They don't have any more or less than that, and no dead cells have any. There are no dead cells with 3 living neighbors, so it's a nice steady state there. And this is pretty cool. And again, this is just looking at each dot's nearest neighbor, so the 8 cells that are around it. And I was thinking it might be fun to try to make a more physicsy version of this, where we take into account the distance between 2 cells. So here I've set up an alternate set of rules where we're going to look at the distance between all of the cells. So we got the same kind of setup down here. We're counting the number of neighbors that are on, but I'm going to expand the definition of neighbor here. So this count on function, I've adjusted this, where we're going to look at the distance between 2 cells along the x-axis and the distance between the 2 cells along the y-axis. And so everybody is a neighbor now. They're just neighbors with different lengths. And so depending on how far away 2 cells are, we're going to add to that count a fraction that's 1 divided by this maximum of the 2 distances along the x-axis or along the y-axis. There are, of course, other ways you could do that. You could do our distance equation, square root x squared plus y squared. But this arrangement here produces some pretty interesting patterns that I would like to show you. So since we're adding fractions together, we can't use those equalities there. We have to put in a little bit of a fudge factor. So for example, here I've set a fudge factor of 0.1. So now we need an equivalent of 1.9 neighbors up to 3.1 neighbors in order for a live cell to stay living. And we need 2.9 to 3.1 neighbors in order for a dead cell to come alive. And so again, we're counting everybody as neighbors. It's just that if you are 2 cells away, you get a count of 1/2. If you're 3 cells away, you get a count of 1/3. If you're 4 cells away, you get a count of 1/4. So you could have a cell that's living with more distant neighbors if you have more of them. That's kind of what I'm trying to get at with this. And it makes for some pretty interesting patterns. Let's try the original glider. So this is the glider I showed you in the previous original version of the simulation. And you can see it ends up dying off, right? Because it's got some of those diagonal elements. It's not staying alive like it did before. So we'll do a slash there. However, I can kind of get a glider with this arrangement with just 4 dots. It's not quite a glider. I want you to see what happens to it. It starts to move along a little bit. It's kind of repeating itself. And then it ends up in this steady state here. So I can end up with this steady state where they all meet the conditions for staying alive and none of the dead cells meet the condition for coming to life. So I think this probably could turn into a glider with a little bit of tweaking. Maybe it just needs another couple of dots somewhere on the board. Of course, now there's a lot more possibilities to try out. Another thing we can try is just lighting up the center portion. So this is what happens when you light up the 9 dots in the center. And this is my favorite one because this produces some pretty interesting stuff. So it fans out this way, then you get the Spider-Man symbol, and then it all goes away. Let me turn down the rate on that so you can see it a little bit better. Should have done that before. Let's click on run. There we go. So we start out with 3 by 3. We get out to this little flowery pattern kind of thing. Then it expands to here. You think nothing's going to happen, and then this little Spider-Man symbol comes up, and then it all goes away. And what's really happening is that there are more cells lighting up around here, or that should be lighting up, but I don't have the grid drawn large enough Let's see what happens when we increase that X max. Let's put 5 more on each side for a total of 50 by 50. I think you can see what happens after that. Of course, now the code is running slower because there's more possible neighbors to check. There's a Spider-Man symbol. Okay, I need to make it wider for this demonstration to work. Let's go out to 40. I forget. I should have made a note of how many it required to see what happens. There's 3 by 3. All right, there's the funny Spider-Man arachnid whatever symbol. And there we go. You see, out in these corners, you end up with cells that are alive, which means there should be cells kind of around here that are alive as well. It's just going to require a much broader grid, broader than I really have the patience to work with right now. So it's kind of interesting. You can get these neat little explosions going on. Let's see what happens when we light up an N by N in the middle. So let's try a 4 by 4 at the start. Oh, there we end up with a square. Ooh, we get a octagon there. Yep, and then we end up going past the range of our grid there, which is pretty cool. So anyway, I don't have really a point to make from this. I just thought it was a cool thing. I think it's a neat way to maybe physicsify this. And what happens if we turn this denominator into the sum of these two? I don't think I've tried that yet. Like I said, I don't have a point with this other than to share it because I think it's cool. So if you find something neat about this, if you are able to turn this into something cool or come up with a great pattern, the code is available in the description below, and I'd love to see what people come up with about this. Here's the original glider. It's going to go down like it did before. Okay, that makes sense. Because I'm making my denominator now just the sum of those two. All right, let's see what happens with my possible glider under this new sum rule. All right, it's kind of dancing around the center there. Oh, then it explodes there. And okay, cool. So we end up with another steady state. Okay, I guess I haven't made enough of a difference in order for it to trigger the fudge factor there. I'm going to comment that out. This should be overriding it, but just in case it's not, let me do that. All right, let's comment that. Let's try the 3 by 3 now. This ought to be interesting because this ought to make a bit of a difference with where this thing goes. Denom is not defined. Oops! Somebody could have told me I had a demon in the code. All right, we'll go back and try those others first. Okay, yeah, so that one just completely disappears under that sum rule. So I'll take those out. What about these? And run. Of course, another thing we can play around with is the fudge factor to make it a little bit more forgiving. Although the fudge factor doesn't necessarily make it more forgiving, because that makes it easier for new things to turn on. And so I wonder if you even need 2 fudge factors, one for switching on and one for staying on, and one for switching off and one for staying on. Here's the original glider. Oh, it's just going to do a little dance there in the middle. That's kind of cool. Okay, so yeah, we can get a little Tetris piece dance there. I wonder what happens. Let's go back to, I tell you what, let's try out this one. This one did not show me too many interesting results. But let's see what happens if we play around with the fudge factor on this. Because like for example with this 3 by 3, yeah, this dissipates after a few moves. Let's see what happens. Let's see what happens if we double the fudge factor just on this rule. Let's see what happens with this. Oh, that's interesting. Ooh, okay. Ooh, that's neat. Oh, wow, we get a circle. Okay, so I'll make a little note here that this one is more interesting if you double the fudge factor. This last one is more interesting if you double the fudge factor just in the, should we call that in the dead to alive rule. And so I guess what I need is 2 different fudge factors. So I probably need a fudge factor for fudge for stay alive and fudge for come alive. There we go, 1e negative 1. And of course now I have to change the name of these fudge factors, so I'll change that one to fudge stay alive, and fudge stay alive, and this one will be fudge come alive. So yeah, so I'm going to continue to play around with this, see if I get anything interesting. You are, of course, welcome to grab the code at the link in the description below. Try out different patterns. Let me know what you get. Would love to see what people get out of this as they play around with it. Thanks so much for watching. I will see you next time. Bye-bye.